Welcome to Exercise 5. In this exercise, our objective is to show the process of digitizing bedding surfaces through both manual and automatic approaches, utilizing various software tools. We will also assess the cylindricity of the structure, establish the optimal viewing direction, and subsequently carry out the orthorectification of a virtual outcrop model. In this exercise, the building and registration of the model have been omitted. The details of the model can be viewed by right-clicking on the model and selecting Show Info. We are now exporting the mesh and its texture. To do that, in the Workspace panel, right-click on the model, and then select Export Model. In the new window, choose the local coordinate system and then press OK. Now we close Metashape and we import mesh into OpenPlot. To load the mesh, from the main menu we select Object, Import Mesh. We select the file, and then we apply the Load Only Mesh option and set the precision to single, which is an efficient choice for saving memory. We eventually save the file in XML format. We now start to digitize the bedding. From the main menu select Plot, 3D View. The first step involves adding a new layer, called bedding. Next, we explore the model, actively searching for well-exposed planes. Once we identify a suitable candidate, we choose the Draw Polyline tool and start picking points of the trace. Eventually, if we are satisfied with the digitized plane, we finalize it into a lasting object by selecting the Create Planar Polygon button. We carry out the process of visual inspection and digitization for all the planes that appear to be promising candidates. After a sufficient number of bedding planes have been digitized, we plot them in the stereo plot. From the main menu, we select Plot, Stereo Plot. In the StereoPlot window, we select Dip Domain, which is the name for the planar best fit element, and plot its poles. Poles to bedding, plot on a great circle. The direction normal to this circle is the beta axis, corresponding to the axis of the fold. Tensorial analysis returns the beta axis, which is the K3, and the direction of maximum concentration of poles, which is K1. This K3 represents the fold axis, and it indicates the direction in which we want to observe the outcrop. In Metashape, we need to transform it into a viewing direction and generate an orthomosaic perpendicular to this direction. In Metashape, it is not possible to set an arbitrary view direction in the orthomosaic menu. To do that, we must use a trick. First, we manually orient the model close to the desired view direction. Then, we open the animation panel and there, we add the current view direction. At this point, we are manually editing the view direction to insert the exact trend and plunge. Specifically, the rules for transforming the trend and plunge into yaw, pitch, and roll, as required by Metashape, are as follows. Now, double-click the view direction to apply it. Recenter the model without rotating it, and update the view direction. Eventually, we export the orthomosaic using planar projection and current view. This will produce the orthorectified model that can be later imported in interpretative software tools. To view the orthomosaic, go to the tab Ortho. To export it, from the main menu select File, Export, and then Export Orthomosaic. An alternative to the illustrated procedure of manual digitization of geological surfaces is their automatic extraction from the point cloud. To do that, we will use the software Cloud Compare. First, we have to export the point cloud, including the normal to point field. The point cloud is then imported in Cloud Compare, where we will apply the Facet plugin. Before applying the plugin, we manually remove all the vegetated areas from the point cloud, as they would return useless results. We now apply the Facets plugin by selecting the point cloud and, from the main menu, selecting Extract Facets. To configure these parameters, users can consult the Cloud Compare guide. Visual inspection reveals that the automatic extraction of planar features captures both geological planar features and some noise. We now export the automatically detected facets and import them into a stereographic software. To do that, we select the facets and save them as CSV file. Then, we open the file and copy only the strike and dip fields. We then paste the strike and dip values in the StereoPlot software. Eventually, we plot these automatically extracted planes. In conclusion, the comparison between the automatically extracted and the manually digitized bedding surfaces reveals significant differences. In particular, an important limitation of automatic detection tools is their high sensitivity to the orientation of the exposure. Nearly planar features, like patches of vegetation or cuts, whether they are anthropic or not, are not mathematically distinguishable from geological near-planar surfaces. With this, the exercise is complete.